race is on. We're on a collective mission to understand and create artificial general intelligence. Dr. Tom Zahavy thinks that reinforcement learning is the most general framework that we have for learning today, and it could lead to artificial general intelligence. He thinks there are no tasks which cannot be solved by simply maximising a reward. Back in 2012, when Tom was an undergraduate, before the deep learning revolution, he attended an online lecture on convolutional neural networks, and he was fascinated with their ability to discover structure and representations. This was an epiphany for Tom. He realised at that very moment that he was going to become a machine learning researcher. Tom's view is that the ability to discover and recognise patterns and structure in data is the most important aspect of intelligence. 2 years later, he started his Ph.D. in reinforcement learning, just 2 months after the DeepMind Nature paper on the Atari games came out. Tom was convinced that reinforcement learning had not yet had its Alex Krichevsky or its ImageNet moment. He still thinks that we need to have something like a CNN in reinforcement learning. This has been his focus ever since. He's particularly focused on diversity preservation and also metagradients to discover structure in reinforcement learning. What are metagradients? Well, to find out, you're going to need to be looking at Robert Lange's recent blog on metagradients. Reading from his blog now. Most learning curves plateau. After an initial absorption of statistical regularities, the system saturates and we reach the limits of handcrafted learning rules and inductive biases. In the worst case, we start to overfit. But what if the learning system could critique its own learning behaviour in a fully self-referential fashion, learning to learn how to learn how to learn? Introspection and the recursive bootstrapping of previous learning experiences. Is this the key to intelligence? If this sounds familiar to you, you might have had the pleasure of reading Eugen Schmidhuber. He said in 1987, I believe in his PhD thesis actually, that every self-referential evolving system should accelerate its own evolution. We can apply meta-learning in the environment we train in, the architectures we use, and the algorithms themselves. So metagradients are the third one, which is to say algorithms. Metagradients are a learning approach that allows us to optimize the inner loop by maximizing the outer loop. We can use meta-learning agents to tune hyperparameters, to learn options or intrinsic rewards or other structure in reinforcement learning. Now, there's a philosophical question about outer loops in general. Should we have an overseeing kind of learning agent in an outer loop, or should we be creating a monolithic approach where we have some kind of reflexivity or self-referential modification? When you fractionate the learning into separate agents, doesn't that just create another set of hyperparameters to optimize elsewhere? Well, this is one of the issues that we'll be discussing in the show this evening. On reinforcement learning, the core ingredient of machine learning is generalization, right? And the learning capacity of a model itself. Reinforcement learning adds several complexities to the mix. You learn by taking actions and exploring in an environment, but you're not allowed to see the outcomes of the actions that you didn't take. Balancing exploration versus exploitation is extremely challenging, and reinforcement learning approaches build on the many decades of literature in multi-arm bandits and Markov decision processes. They introduce many important dimensions into the process that didn't really exist with supervised machine learning. Reinforcement learning also introduces the concept of credit assignment or sparse rewards, which means that your learning signal might not be given for a very long time after you take action in the system. Next, you have to overcome deceptive search spaces, which is when you can no longer trust your own compass to be optimizing in the correct direction. Deep exploration, or even exploration with deep neural networks, is something that just hasn't really been solved yet. Sample inefficiency and generalization are core challenges. Last but not least, the training dynamics are non-stable in many reinforcement learning configurations, and some of the more sophisticated use of reinforcement learning, such as gradient clipping or shared representations or auxiliary tasks, these can kind of saturate the learning capacity of the agents, introducing even more non-stationarity into the learning dynamics. Now, metagradients are one of the ways to combat some of these significant challenges in reinforcement learning. Metagradients allow our agents to discover their own way to represent the world, to create agents which discover structure and can adapt to their learning environments dynamically. The fascinating realization for Tom was that getting the meta-agents to imagine a non-stationary reward actually allows the inner agent to solve more complex problems, for example, a constrained Markov decision process. So metagradients give you an optimizer that works even better on non-stationary environments and learning dynamics. We still see a bias variance trade-off for many of the key architectural design decisions that we make in these learning systems. For example, which type of gradient do we use, or how many steps do we take in the multi-step optimizer, and whether we use the same data or different data in the loss function. Tom says that self-tuning with fewer parameters implies that less variance is important, whereas learning an intrinsic reward as a kind of DNN with many parameters implies that less bias is required. Now, metagradients have demonstrably improved the learning dynamics of reinforcement learning algorithms, and it seems that the more metagradient parameters that you add, the better the performance. Tom also really likes the idea of options as a way to model temporal structure in reinforcement learning. Now, Tom mentions the word options a lot in today's conversation, and if you haven't heard of options, you can think of options as being kind of a category of trajectory in the state action space, so attending a meeting or visiting a certain room in a game, whereas actions are the primitives that can be composed to construct options. Anyway, I really hope you enjoy the show today. I've learned so much. Anyway, remember to like, comment and subscribe. We love reading your comments, and we'll see you back next week. Welcome back to the Machine Learning Street Talk YouTube channel and podcast with me, Tim Scarf, and Yannick Lightspeed de la Kilcher. Today we have our regular staff member, Robert Lange. Robert is completing his Ph.D. at the Berlin Institute of Technology. As we've covered previously, Robert has arguably the best blog in the machine learning space, which is robertlange.github.io. He recently published Meta-Policy Gradients, a survey where he investigated the state-of-the-art of second-order policy gradient methods. Also joining us this evening is Dr. Tom Zahavy, a research scientist at DeepMind in London. He's previously done stints at Google, Facebook, and Microsoft no less. He holds a PhD in machine learning from the Israel Institute of Technology. His bachelor's was a double degree in electrical engineering and physics from the same institution. Tom was the primary author of the ICML paper, Graying the Black Box, Understanding DQNs, where he established that DQNs aggregate the state space in a hierarchical fashion. Tom also wrote the paper, Is a Picture Worth 1,000 Words, from 2018, on using a policy network to switch between multimodal product classifiers. In 2016, Tom was also involved in the well-known paper, A Deep Hierarchical Approach to Lifelong Learning in Minecraft. He was also the author of Learn What Not to Learn, Action Elimination with Deep Reinforcement Learning, and in this paper, Tom established that sometimes it's best to learn which actions not to take. He used an action elimination network to achieve this. And more recently, in 2020, Tom wrote a paper called A Self-Tuning Actor-Critic Algorithm, where he applied metagradient methods to self-tune the hyperparameters of an actor-critic loss function. Now, quoting from Rob's recent blog post, what if a learning system could critique its own learning behavior? Schmidhuber said that every self-referential system should accelerate its own evolution. So, Tom, it's an absolute honor. Welcome to the show. And why have you been drawn to metagradient methods recently in your research?
Hi, Tim, and thanks for the lovely introduction. So the reason that I started to work on metagradients is related to like my big perspective on how we discover structure in machine learning. And I think that it should be a combination of basically three things: the environment that we train in, the architectures that we use, and the algorithms that we have. And I think that metagradient is a part of the third aspect, the algorithm. So basically, it's a method that allows us to learn something different in order to solve a problem, while getting better and better in solving the real problems that we want to solve. And as a technique, we can use it, for example, to tune hyperparameters, to learn options or other structure in reinforcement learning. And the nice thing about it is that it kind of gives us a very flexible framework to do many things.
Could you give just a bit of your intuition about what the word meta in the meta policy gradient really means? What does it mean to you, and what's the appeal behind it?
Yeah, a perfect question. So if we look at what is an algorithm, like from a higher level perspective, it's a process that drives us to learn representations or to learn predictions. So we get better and better at doing a task. And if we look at what people were doing from the theoretical point of view, then we look for algorithms that will work in general on any kind of environment. And as a result, we have to sacrifice something. Like we can't be as best as we can on a single or on a particular environment. So if we look at what we are doing in metagradients, we basically want the algorithm to adapt to a given environment, and in this specific environment, get better and better and learn at learning while it is learning to solve the problem. And what is unique about metagradients compared to other work in meta learning is that we basically assume that there is only a single environment. You don't need this notion of having train and test environments. Everything happens in a single environment, and you try to get as better as you can for this particular environment.
Can you maybe give us an overview of the different types of metagradient methods that were developed in the recent years? So starting with the original paper from 2018, and then sort of, your progress and the recent paper on options you spoke about. What are the differences and how do they all tie together?
So I think the first thing that we need to distinguish when we talk about metagradients is what are the parameters and what are the metaparameters. And as we start learning more and more things, as we start to learn intrinsic rewards and start to learn options, this distinction becomes more and more vague. Like what should be learned with the direct gradient and what should be learned with the metagradient. The first work by Zhongwen Xu focused only on hyperparameters, the discount factor and the lambda return parameter. And then roughly at the same time, there was also a work led by Zeus Zheng that tried to learn an intrinsic reward. So straight from the beginning, we had these two lines of work, one that tried to discover a specific structure for reinforcement learning, and the other one that focused on self-tuning or on trying to learn hyperparameters. The second distinction that we usually make is between white box methods and black box methods. In the white box methods, we usually try to meta-learn some aspect of the reinforcement learning algorithms that we understand very well. It can be the hyperparameters of the algorithm, or it can be the intrinsic reward, but it's something that we already have good intuition about, and we know algorithms to optimize it. When we go to black box methods, the idea is basically to replace all of this human intuition and just let the machine to learn everything. So we can model the entire loss function of the agent with a neural network and see if this approach can discover a new algorithm. And I think that as you go on this axis, like when you do white box metagradients, you understand things very well, you know where to start. So you can do things that are very close to be a good solution. And as you go to black box methods, you get farther and farther from having a good initialization point, but you also have the opportunity to discover better things or more novel things because you don't have this prior on what you do.
It's interesting that you frame it as there is only one environment, so to say, and you're trying to get better and better at learning in this one environment. And I think a natural question is, why don't you just run like one big learning run? Like why, if there is only one environment, why do you have to get better at learning in that environment? Why can't you just, I take my mu0 or something, my super big RL algorithm, and I just run it once for a long time with all the resources that you would spend on meta learning the reinforcement learning algorithm. what's the difference between sort of really learning one environment and learning to learn if there is only one environment?
I think we are basically taking both of the approaches. So I think, and that's basically the last distinction that we make with respect to metagradients, is the single lifetime versus multiple lifetimes approach. So the multiple lifetime is more a classical meta-learning approach where you have these training environments, you try to learn a better rule, and then apply it on a test environment and see if, just by training on some previous task, you get better at learning on future tasks. In the single lifetime type of works that, my work on a self-tuning actor critic is one of them, we are basically doing everything in a single lifetime. So it basically falls under your description. I think that the reason that we are still training it on a suite of environments and not only on a single one is basically because we don't have like an environment that perfectly models the world. So basically, we are limited by the environments that we currently have, and if we want to test the generality of the approach, and we don't have this single environment that gives us all of the aspects that we wish, then we can instead, run many instances of it on different environments and learn more about the generality of the algorithm by doing it.
So I have one question regarding sort of the transfer capabilities of what we meta-learn in this case, right? So in a single lifetime, you oftentimes have sort of a schedule of hyperparameters that pops out of these metagradient approaches. And in the multi-lifetime sort of Blackbox cases, you have a neural network that might parameterize an entire objective, and they're no longer these single parameters. And to me, maybe correct me if I'm wrong, when you're in the Blackbox case, it's a lot more clear-cut how to transfer this discovered objective than in the case where you have these discovered hyperparameter schedules, because they are sort of more overfit to the problem that you're actually trying to tackle.
Yeah, we really need to think about like this distinction between transfer and learning in a single lifetime. When you learn in a single lifetime, you basically want your algorithm to overfit to the specific environment, because you want it to learn as good as it can in this specific instance. And if it's the world, then you're done. Like if you have a system that learns to learn better and better. So in this case, I don't think that you want to freeze something and transfer it to new environments, because you want to still have this possibility to adapt to the given problem at hand. When we talk about the classical meta-learning approach, where you have the training tasks and you want to transfer something to new tasks, then it makes perfect sense. And then basically the idea is that, as a community, we work on these very defined benchmarks for a long time, and we develop intuition and algorithms for solving them. And the question is that if we can replace this part by a black box algorithm that just learns an algorithm by its own. And I think that, it poses two different research questions, and both are interesting.
When it comes to meta learning, especially in the more classic sense, where I say learn the hyperparameters of an algorithm, or, I learn kind of the loss function and so on, I think a natural question is also the algorithm that you use for this. So the meta algorithm naturally is also going to have some hyperparameters, is also going to have some sort of, intuition behind it and so on. So isn't it just shifting the problem to a higher level? And why can it make sense to shift that problem? Why is it easier to tune the meta hyperparameters in a sense?
It's also a very good question. I think if we take a step back and look, at what other communities have done on this type of literature, then the origins are in bi-level programming and online within online meta-learning. And then, let's take, for example, the online learning literature. If your distribution has some properties that, are not the worst case over the entire world, then you can hope to get something by doing meta learning. So for example, there's a very good paper by Nina Balkan, and they show that, for example, if all of the optimal solutions are in a small area in the solution space, then you can get accelerated learning just by doing meta learning. And if I zoom back to metagradients, the optimizers that we use for optimizing the meta parameters are really, the default thing to do. We use Adam with kind of a standard learning rate. And from my personal experience, it wasn't too hard to, tune it, or I didn't spend too much time on doing it.
Could I slightly reframe what Yannick said? Because I think in two questions, Yannick is basically asking the question of, should a monolithic approach suffice, or should we have a modular approach? And we have this argument all the time in software engineering, for example. There are pros and cons. What are the pros and cons for having a modular approach and having essentially an outer loop, which is separate?
If we go back and think on why do we need these two loops, and why we can't just learn everything end to end with a single optimizer, then the metagradients, they allow you to do something different in order to solve the problems that you care about. And the framework to think about it is regularization. And if we think about, how people solve supervised learning tasks, then we have the training phase, the cross-validation phase, and then the test phase. And basically, we allow ourselves to optimize something else than the objective in the inner loss, or when we do training, which is a regularized objective, and then to choose the one that is doing best in the outer loss, or on the cross-validation loss, which is an approximate to what we really care about. And the reason is that, some models are bounded. We can't find the optimal solution with any approximator. So we really need regularization. It's a very established principle in machine learning. And metagradients give you this flexible framework, but they do everything online. So it's different, from traditional cross-validation, because you're kind of doing online cross-validation by doing gradient descent.
So what hinders us from just adding more levels to this structure, right? So in principle, you could think of adding another layer and using metagradients to optimize the hyperparameters of the meta objective, right? And in some sense, I'm wondering, is the main limitation in an explosion in the variance of the gradients? Is it an optimization problem? Or is there something different that sort of hinders us from doing this?
Yeah. There are many, technical issues in implementing these systems. And I think that, the line of work that we did on self-tuning focused on stabilizing everything, showing qualitative properties like stability and robustness and adaptivity from what you can gain from doing these methods. And I think that the most interesting thing that you can wish to gain from metagradients is this ability to have a non-stationary optimizer while you're solving a problem. If you think, only on supervised learning, then you might not need to have a non-stationary optimizer. But if you go into the RL setup where the agent discovers its own data and the data distribution changes over time, then you already have some non-stationarity in the environment or in the learning dynamics. Another example is constrained MDPs. So if you want to solve a constrained MDP, you need to deal with a non-stationary reward. And then the agent is basically making the word non-stationary to solve the problem. And you have inherited non-stationarity that you need to deal with. And in that case, we also think that metagradients really help. And the last aspect that you refer to is stuff like doing gradient clipping, or another example is shared representations, like if we share the layers between the actor and the critic and maybe some auxiliary tasks, then there are cases where the capacity of the agent might not be big enough to approximate the optimal solution. And because you are sharing things and because you're using gradient clipping, you are kind of introducing a competition on resources between all of these different objectives. And in that case, it's another example for why an agent is kind of introducing non-stationarity into the learning dynamics, and metagradients might help to balance things.
Okay, because in my mind, the reinforcement learning problem was always harder because of the non-stationarity, and supervised learning, where you have fixed targets and a fixed target distribution at which you just need to shoot, essentially is easier. But what you're saying sounds more like essentially that the additional non-stationarity that you get from the meta policy gradients is more beneficial in the case where you have already non-stationarity in the inner loop, because it can sort of counterbalance it. Is that sort of?
Yeah, exactly. Like if you have to deal with a non-stationary problem, I think that there's more hope to gain things from using metagradients, which are non-stationary by themselves.
Is there so now we're talking about having this outer loop and an inner loop, and potentially having outer loops around the outer loops, right? Could you a little bit talk about maybe efforts to not really have this layer, this level structure, but about optimizer that directly self-modify, right? So if I have an algorithm that not only does it optimize some kind of inner agent that essentially knows nothing about the outer agent, but you could imagine a system where the meta algorithm directly, right, modifies its own parameter, its own hyperparameters. Is that a feasible direction?
I think that from the theoretical point of view, if you go back to this online meta-learning papers, basically you can do something like that. I'm not sure if when you'll go to write the code for doing that, it will look that different from the outer loop formalism that we have and the way we do implement it at the end. Because when we think about the outer loop is basically a way to say what is the gradient that we want to take for the meta parameters to improve our learning the parameters in the inner loop. So basically we need to have this, taking gradients of gradients approach, which is anything that, the meta gradient line of work is about. So I guess, you can find other ways to optimize that. But I'm a big believer in gradient descent and methods that do gradient descent. So I personally think that it's, the more promising direction.
And maybe also a follow-up question to this. I don't know if you've seen this work by Luc Metz. So Luc Metz had this year, I think, a very short paper on learned optimizers by sort of improving on themselves, right? So this very classic Schmidt-Huber idea of self-referential bootstrapping, essentially, right? And in that paper, they showed that the learning dynamics are apparently not too bad, and that you can actually learn optimizers by sort of starting from a random initialization, right? And what they do is they have in the outer loop, I think, evolutionary strategies, so some form of approximation to the actual gradient. Could you say something about how or why are you using the true, I guess, analytical gradient calculated by autodiff packages and not an evolutionary strategy instead? Is there some reason? Is it variance?
Yeah. I'm a big fan of theory, so I like to read a lot of theory. And if you look at the origins of evolutionary strategies and the concept of creating noisy versions of your loss function and computing a numeric gradient from them is actually well established in the convex optimization literature. The main thing that evolutionary strategies give you if you have a convex loss function and everything is well defined is that if the function is not differentiable and so the noisy versions give you an easy way to compute an approximation to the subgradient. And then if we go back to what this type of methods can give you that metagradients cannot, they can help you to differentiate metaparameters that are not differentiable or that can't be represented as a differentiable function of your loss. And there are quite a lot of examples for metaparameters like that, like say the bet size or the size of your experience replay.
What are sort of parameters which we want to leave untouched by metagradients, right? So you spoke about experience replay buffers, and for example, there you have two hyperparameters in sort of the amount of prioritization you want to do and the amount of important sampling correction that you want to do, right? And in some sense, the way how they go in is you would have to sample a batch according to the distribution that you get from these parameters, essentially, and some temporal difference error. But then you would have to sort of propagate gradients to the stochastic sampling that's involved there, right? Is that something that you want to leave untouched? Or, yeah, what are the limits of metagradients when looking at the set of all parameters that you have in reinforcement learning algorithms?
So one of the things that we tried to achieve when we wrote the self-tuning actor critic paper was basically to show scalability. Like to take these ideas that John Gwen developed in his first metagradient paper and to show that as we tune more metaparameters, we basically get better and better. And we did a very careful, ablative analysis on that, and we were able to show that, the performance just keeps improving as we self-tune more hyperparameters. That said, I do think that, there are some metaparameters that you might not want to tune. And the reason is basically more related to how you evaluate the metagradient. So as you said, like you collect a batch of data. This data is usually, if we think about this Impala agents, then this data is at some level off policy because it is generated by previous actors. And so then, for example, if you try to self-tune some off-policiness hyperparameter, you have the problem that you can't evaluate it on the things that you really care about, which is, like the on-policy performance. So there are many challenges, like to get it right, but I'm a big believer of trying. So like you can expose more and more metaparameters if you have a flexible code base. And if you see that some things work, then you should think very good with yourself why. But I don't like to put barriers before I see things.
Could I quickly touch on Robert's previous question about the evolutionary methods? Because I'm a huge fan of Kenneth Stanley, and he's one of the biggest advocates of neuroevolution and open-endedness and diversity preservation. And he uses the example of a maze. When you have diversity preservation, you can overcome deceptive search spaces because you kind of allow all of the different agents to go down a deceptive search path for longer before you kind of kill them. So that seems like a really good thing for me. I didn't quite understand why you said that wouldn't be applicable here.
I actually said it will be applicable, so let me re-clarify myself.
Sorry.
So I think that, specifically evolutionary methods or the ones that were used to tune by OpenAI, like a DQN agent, this type of methods basically work on creating noisy versions of your parameters and then producing what is basically a subgradient of the loss function and doing a gradient step using this approach. So it's a very good example for a method that started in the evolutionary community with very good intuition, but basically have very well-founded foundations in the convex optimization literature. So I think that, it's a method that should work. It's applicable for metagradients, and it also gives us the possibility to tune non-differentiable hyperparameters, which is something that, we can't do out of the box with metagradients at the moment. So I do think there's a lot to gain from trying that. I'm also a huge fan of diversity, and it's something that I'm working a lot about lately. And I think that, diversity has a human quality in it. So if you think better, why do we need diversity in NI? Can we just find the optimal solution? If we can do it, why do we need more solutions? Why is one not enough? And I think that the key is that as humans, we can never find a perfect solution. We are always bounded. We have limitations. And if we acknowledge that, then finding more solutions that are diverse, which are, not necessarily the things that we think are the best, but maybe something that someone else thinks is the best, is a good strategy for dealing with that. So again, I like things that come from the convex formulation. So I think that there's a big hope to also optimize diversity, with convex methods or with gradients. It doesn't necessarily have to be an evolutionary method at the end, but the type of methods that you choose to work is basically the ones that you are more excited about at the end.
With optimizing diversity, though, there is what people usually do in reinforcement learning is they add something like an entropy regularizer or something like this, and it always appeared to me like that would give you some diversity in solutions, or also what you said, what DQN does, which is you do some kind of a noisy version of your parameters and then you evaluate that. It always seemed a little bit not really satisfying to me, because essentially what it does, if you have your solution kind of attractor base into the the solution that is given by the gradients, it seemed to me like these types of things would just sort of fuzz this a bit, like give you kind of a Gaussian bump around it, but not really go for the types of diversity we see in these these evolutionary algorithms, where you really diverge in not only like a little bit, but fundamentally different approaches to solving problems. Do you have an opinion about what can except for evolutionary methods, what can get us to like really qualitatively different solutions to problems?
So I think the question is where you want to end. If you want to end with, for example, a set of policies that solve a given problem at different ways, then there is a way to formalize that. If you look, for example, at the line of work on variational intrinsic control and diversity is all you need, so this type of works basically try to maximize the entropy of the set. So you want policies that visit different states. And if that's where you want to end up, you can actually write, a convex problem for doing it and optimize some intrinsic rewards that will lead you to get there. We had a recent paper in iClear trying to do something like that, more from a robustness perspective. The mutation part or the evolutionary part is a process that can give you that. It's usually harder to give guarantees on how fast will it do it or how will it scale. When you start to work on things from the optimization point of view, then you can get better intuition on are you doing the right thing or how much time will it take you to reach this optimal diversity that you want. That's why I'm like a bigger fan of this type of methods.
So something that I discovered in multiple pieces of your work is that in some sense in stacks, there are multiple tricks how to render more of the reinforcement learning pipeline to be exposed to metagradients, right? So you make the vtrace sort of operator differentiable, and you add multiple heads to your architecture to have sort of more parameters to tune with metagradients. And is there sort of, what's your mindset when figuring out these things, or how do you approach the problem of getting the most out of metagradients?
I think you should always be motivated about something. And when I started to work on StackX, my motivation came from this idea of learning with multiple discount factors. There was, work on that before I started to work on StackX with good examples on Rainbow Agent. And if you think more deeply about it, a discount factor actually approximates the planning horizon of the agent. Like that's the horizon that you are willing to make your plans up to something that goes like 1 over 1 minus the discount factor. So if you think about games like chess, if you are limited by your planning horizon, you will get up different plans or different chess strategies. And this general motivation was what motivated us to start working on StackX, because we believe that, if we'll have many discounts, then maybe some of them will decide to be shorter. They will allow us to discover shorter plans on how to be locally optimal. And maybe making these predictions will make it easier for the agent to derive larger plans or deal with harder problems. And I think that, in all of the metagradient works, we always started with a problem that we understood very well. If it's the intrinsic reward work, if it's the options work. So it was a problem that we studied for a long time in the reinforcement learning community. And then the metagradient instance came to deal with, certain tuning aspects or certain details that, we didn't like to be too much obligated to have them pre-tuned or predefined.
In one of the figures where you show essentially the different hyperparameters for these 3 heads, right? It seems like the first head, which is the one which acts in the environment, has a very distinct hyperparameter, like a larger discount, while the other 2 sort of have very similar hyperparameters. And I was wondering, in some sense, why is there then the third head if basically just the second head could do the job? What is different about the learning dynamics? Yeah.
We did try, to run it with other configs or to search over this number of auxiliary tasks. This was the main new hyperparameter that the architecture had. Because when we add this new auxiliary task, that's basically the only thing that we need to add as a new hyperparameter, because everything else remains the same. 3 worked better than 2 and better than higher values. So it was an empirical finding. But if you look at how these hyperparameters tune, so you are correct that in many of the games they tune exactly to the same values, but not in all of them. So we were able to find games where each one of them tuned to different values, and the algorithm was able to discover these different, 3 different planning horizons.
Taking a step back before you said, Robert said something, maybe you want to leave the batch size alone because you need to sample differently, or there are some parameters that are tricky to get from the discrete domain to the differentiable domain. There are approaches where you just try to learn proxies for these things. Like you try to learn, so instead of making the things differentiable, which is what you usually have to do in meta learning, you try to learn some kind of proxy neural network for them, which is differentiable, right? Could you tell a bit about how do these approaches usually work, and why don't we use it for all the things that are not differentiable? Because it seems like a good idea. Just have my neural network there that approximates it, and bada boom.
Yeah, it's a great idea. I don't think there is any reason not not to try it. It's actually something that has been on our minds to try. I think that the complexity of your system will grow when you'll stop doing things with gradient descent. So if you need to approximate non-differentiable things, it will require work and more tuning to get it to work right. While the metagradient type of work, when we focus only on the differentiable things, is really quite simple. So I'm just saying that there's a bar that you need to cross if you want to go to this other regime.
Yannick, could I put that back to you though? So if you did have a surrogate model which described a model which was non-differentiable, and then you took the gradient of the surrogate model, if the model was basically just memorizing lots of stuff that it's trained on, why would the gradient of that surrogate model be meaningful?
Well, you'd sort of, if you think about the batch size, right? You just kind of run a bunch of runs with different batch sizes, and that automatically gives you a training set for a neural network that has the batch size and maybe some other parameters as an input, right? And then it has as an output something you care about, like it could directly be the performance, or it could be the output for some other part. Like, for example, if you tune the batch size, the output could actually be the batch, right? Because that's what your sampling process, it takes a batch size and gives you a batch, right? So you could train a neural network in principle to take in the batch size as a number and output a batch of data. That could be, actual data, or it could be data in latent space, already at like layer 1 or 2 of the neural network that it's going into. But technically, it's feasible to train that. And then you could perfectly, right, backpropagate and predict what's the optimal batch size, or how do I need to adjust my batch size to get a better training signal. But I see that the complexity, of course, is huge in that, because, and it depends on how accurate such a surrogate model can even be. But, given the fact that deep learning has been super duper successful in so many things, it might as well be successful in these things.
And I mean, I think there are also multiple examples in neuroscience where people use surrogate gradients or surrogate models to approximate the discontinuity of spikes, right? Where in the forward pass, you treat it as non-differentiable and just have your step function. But in the backward pass, you put something smooth over it, essentially, right? So you have different forward and backward operations, essentially, right? And I think synthetic gradients are another example where people try to make this work, right, to a certain degree. Coming sort of back to a point that we had in the beginning of sort of multi-lifetime versus single lifetime. And in a single lifetime, you want essentially to overfit to the environment that you're sort of tasked with, while in the multi-lifetime, you want to be able to transfer, essentially, right? And I was wondering, another key difference between these two is that in the one case, you do the sort of the online cross-validation that you spoke about, Tom, on the train environment, and in the other, you do the online cross-validation on the test environment. So that in the multi-lifetime case, the test environment really sort of dictates what the metagradient essentially tries to distill into the optimization process, right? Can you talk about sort of design choices of what test environments to pick, or how should I choose the set of environments so that most of the RL specific optimization problems or problems are sort of captured?
So like, I think this answer basically also answers the previous question by Yannick. Like, I think that with this type of techniques, we should be able to learn everything at the end. So if our training suite of tasks is wide enough and the real world is, and it captures the real world at the end, so we learn long enough, we can basically, learn everything that we want. But then, when you take back and you zoom into what we are currently doing, then there are limitations. The environment's maybe not diverse enough to represent the test perfectly. Maybe we just, in a single lifetime, maybe we just need to learn things fast enough so it becomes useful and improves the performance. So it doesn't say that, if we'll have 10 times more budget, we can't learn more things. It says that, from our experience in the, feasible frame budgets, that's the things that we were able to learn. And it's a trend that you see all over the machine learning or the deep learning community, that you're basically, limited by your data in what you can discover. In the metagradient case, it's a bit different because the agent discovers its own data. But when you think on the meta parameters, you do need enough time for the algorithm to pick up. So the only question is how easy to learn these hyperparameters so it will pick up fast enough.
Looking at your Google Scholar profile here, the most cited papers of yours is actually the deep hierarchical approach to lifelong learning in Minecraft, which always makes me wonder whether or not I should convert my channel into a Minecraft channel. It would probably be much more popular. Could you talk a bit, because that is it. What's special about it is it from 2016, which is, it's like a lifetime ago in terms of it's one PhD ago, right? And a lot has changed since then. What could you describe a bit the paper and what you did there? Because like, did we even have we had ResNet, right? But it was still like limited.
Yeah, so it's fun to go back in time to these days. So just to give a short intro, like I was a PhD student in DeepRL before, it was after DeepMind released the first ICML paper on DQN, but before the Nature paper went out. So everything was like magic in these days, and I had a single computer with a single GPU, and I ran DQN, and I saw it play, and I stared at it for hours, like trying to understand what it's doing and how it's playing. And I was reading, other literature on reinforcement learning and specifically on structure, because I was interested in discovering structure. And I really liked the idea of options and as a way to model temporal structure in reinforcement learning. But we didn't have, environments that we can control or we can ask very well, carefully picked questions in them. And because of that, Minecraft was appealing, because we could basically build our own worlds in it and ask questions about it. And there was no, Zoom, Doom or DMLab environments at this time. So what we did is basically we supervised an undergraduate student project. And the first authors of this paper were undergraduate students working on Minecraft at this time. And they built everything in Minecraft. And the agent interface that we used for this paper was actually doing print screen to capture the image input for the agent. So it was that preliminary in these days. We later switched to use the Malmo wrapper, which Microsoft released after we wrote the paper. So we did reproduce everything like, with a normal input. But it was like very exciting days because it wasn't known what is possible to do, what is not possible to do. And this specific paper tried to, to introduce options or to introduce HRL into DeepRL agents, which was something that, was not possible at this time. And to show as a proof of concept that we can do these things.
If you think about something like Minecraft, and if you think about how humans go about, playing Minecraft, essentially, of course there is an aspect of, let's say, meta learning in that I go look up on the internet what other people do, right? But essentially, you could give me a copy of Minecraft, and I could, get along fairly well in there, play a bit, and I would never have to restart the game, right? Unless I play on hardcore. But, I die, I wake up again, I try again, and so on. And this is more, as like the paper is also called lifelong learning. What are your current thoughts? What is, if you had to design, maybe not constrained really by current compute, but not NP hard. If you had to design the perfect algorithm for lifelong learning in something like Minecraft, what would that look like? If in your mind, from what you've learned since then.
The interesting thing about Minecraft is that, as a human, you don't have explicit reward in the game, right? Like you can basically do whatever you want. But the thing is that, as humans, we do have some intrinsic motivation to do lots of things. And we get joy, by building things or getting to new areas. And it's a hard question to think about an AI in this game because, it doesn't come with all of this intrinsic motivation unless you code it. And now there's a question if, when you are going to build an agent and you want it to live in this world, are you going to evaluate it as a human? Like, are you going to say this AI is intelligent because it's building things and doing things that I care about? And if so, how do I tell it to do it? Like, how do I encode the intrinsic motivation that I have into the agent? And do I give it as an extrinsic reward? Do I give it as a mechanism to discover intrinsic rewards? So that there are many questions to think about here. I think that we need agents that are able to discover these intrinsic motivations. But I also think that the world should have lots of rewards. Like I personally think that the world have many dense rewards, and the challenge is actually to choose between all of these sources of reward, and I don't think that as humans we experience the world as a very sparse reward game where we only get feedback when we finish goals. So the metagradients does come into the picture here because we can have this very rich mechanism that allows the agent to learn these intrinsic rewards and find its own way to define sub-goals and options and all of these things that we did in order to get better in living in this world.
But so how would, and I'm thinking more about the real world AIs, right? Because I've for a while I've been thinking about something like, let's say, big companies like Google or something like this. In a sense, they are sort of organisms too, and they are organisms, and you can say, okay, we live in capitalism, but it's not really true, right? Because they in a way, because they're also monopolies, they shape the structure of the market themselves. So, and an AI that lives in the world, do you think we could even recognize something if it wasn't explicitly made to be human? Or do you think that would be recognizable? Or will we just think like this stupid computer is doing, I don't know, like what would a self-discovering intrinsic reward system look like, and could we recognize it, or do we need to explicitly say it must be like a human?
Yeah, it's a great question. I think the general question is that how will we reach AGI, or like even is that possible? And then the question is like, when will we say that something is an AGI, right? Like if it will do things that look to us intelligent, we'll probably say that it is. But then let's say that we discovered an AGI, and you now let the AGI to discover a new AGI. Will it have the same test like for intelligence, right? And I think that not. Like I think that there's no one formulation or one definition for intelligence. Like we perceive it in a certain way, and we'll consider intelligent things that do this type of things. But we should not constrain the AI or the AGI at the end to be like us. The more tricky question is how do you reach that, right? Like what is the path to reach AI or AGI? And there I think that, we are limited as researchers to things that we are excited about, to things that we think are intelligent. And to reach that, we must have some level of interpretability or criticism to say this thing is doing the things that I think are intelligent. I think that also diversity gets into the picture here because I think that at the end we want the AI not to only be good, at maximizing scores. We want it to look more natural to us, to be more creative, to do other things that we are able to do as humans. And if we, care about these things from this point, when we'll reach some level of AI, it will have other human qualities in it as well, and not only the characteristic to solve things.
Just to touch on that, because we've got Francois Chollet coming on the show soon. I'm not sure if you've read his Measure of Intelligence paper. I'm only allowed to invoke his name once per show, so I'll do it now. But he says that intelligence is embodied, so it's a process, it's not a brain. And he says that intelligence is the information acquisition, efficiency, and generalization. So in a roundabout way, he basically says that reinforcement learning isn't intelligence, because intelligence must be normalized by any knowledge and experience that you give it. So in a way, he's kind of trolling reinforcement learning. I mean, do you have any opinion on that?
I think that, the foundations of reinforcement learning are definitely about intelligence. It's about how fast you collect your data to get better and better in the world, and how you, diminish your uncertainty about the world and get more and more information about it. So it's definitely about intelligence. I also agree with the point that, a brute force approach for planning is not intelligent. And you see examples for that in chess, chess was able to get better than humans, right, with brute force approaches, but Grandmaster didn't thought that the chess engines or deep blue type of chess engines are intelligent. And when we tried to tackle a harder game like Go, we weren't able to do it like with a pure brute force approach. And we had to get some learning or some pattern understanding into these machines to get better and better at more complex problems. So I completely agree with the idea that we should discover patterns and we should use information efficiently. But I think that, reinforcement learning is all about that. So
maybe then the completely contrarian opinion is David Silver's hypothesis on reward is all you need, right? In the sense that for him, I hope I don't misrepresent this here, the reward or the reinforcement learning formulation is basically everything that we need to capture intelligence in some form of way, right? We might not have the right tool set right now, the right algorithms, the right architectures, what you spoke about in the beginning, but do you think this is a different point of view that one can arguably have? Is there something missing from sort of the problem formulation that we have right now?
So I don't think it's in contrary at all. I think that, reinforcement learning is very general. Why it's general? Because, it has the generalization aspects of supervised learning, but it's adding to the equation three more important things. One is exploration or online learning, which is about how you learn from actions if you're not allowed to see the outcomes of all other actions. How do you do balance exploration and exploitation efficiently? So reinforcement learning is basically building on everything that was done in the bandit literature and later in the theoretical community on MDPs to have another aspect that, classical supervised learning systems does not have. And the third axis that is important in reinforcement learning is the credit assignment. How can you learn about the actions that you take on the present from outcomes that you see in the future? So each one of these aspects, like exploration and credit assignment, basically take the basic, supervised learning theory point of view on how systems learn and extends them like in two aspects. And now you can say, like, are there problems that I can't solve with these three ingredients at hand? I think that, metagradients or online within online meta learning is one way to extend it. And there might be others. But the question that we need to ask ourselves is, are there problems that we can't solve by maximizing reward? And I'm not sure that there are. Like if you look at the convex optimization foundations again, then you can solve any convex problem if it's defined on an MDP by maximizing reward. by calling to a linear, you can think about maximizing reward as calling to a linear oracle, and then you can basically do things like Gale or solving constrained MDPs. All of these more complex problems were basically solved at the end by maximization of reward. And I think it's an interesting point because it's basically very general. Like I think that finding instances that you can't solve by maximizing reward is going to be hard. I'm not saying that there aren't, but I'm saying that the framework is perhaps the most general that we have at the moment.
On the reward is all you need. I also don't think there's any conflict there. I think what Chollet points out are two things. It's the fact that to build an intelligence with that framework, you would need to have unlimited priors and experience. But the other thing Chollet talks about, I think he's focusing in on the substrate of neural networks. He says that the type of generalization you have in neural networks is what's called a kind of continuous generalization. And he wants to move to something called a program-centric generalization, which is thinking about reusing modules in graphs, thinking about programs as being graphs and being able to identify isomorphisms in graphs. And he thinks that that kind of generalization in topological space will be significantly better than using the substrate of neural networks.
Yeah. So, I started to work on deep learning when it was not that popular. And people questioned, like the generalization capabilities of deep networks for a long time. I think that we are starting to understand better on how deep networks generalize. Like if you look at the double descent curves or the lottery hypothesis, people start to understand better why these interpolations that deep networks do between the points that they memorize is actually something good and it can generalize very well. I don't think that we have the best theory at the moment on how they do it, and it's possible that people will come up with other structured ways to capture patterns and generalize with them. If someone is excited about trying other ways, that's the way to go. Like even with deep learning, it started by people saying, don't do that. So like if someone has a new idea and he wants to replace that part, I wish he will succeed, and will progress as a community. Personally, I believe that, at the moment, that's the best models that we have. And that's why I'm excited to work with them, because I like to build things and see what they do. I think that looking at how to discover structure is the main thing that drives us forward in the machine learning community.
Like a couple of months ago, Sara Hooker had this blog post on the hardware lottery, right? Where she spoke about how the current sort of state of the hardware that we have is very much influencing the scientific ideas that we try out, and sort of also the scientific ideas which never make it to fruition in some sense. And when I look at most of the metagradient work, it's very strongly built on JAX and on TPU support. Which ideas are we missing, or which ideas are there still sort of looming in the metagradient work or world, or sort of which ideas are the ones that can most benefit from the hardware that we have right now?
So there's definitely a correlation in the community, between the software and the hardware that we have to the things that we can solve. I think it's also a matter of excitement. Like once you are very excited about an idea, you'll start to develop a code base, and if you can make other people excited about it, then you'll get support from the community and will develop new software for doing new things. JAX specifically is amazing for its autodiff capabilities and its vectorization, and it makes things with metagradients much easier. Like it's not that they weren't possible before, but what we did before was basically to compute many of the gradients by hand and then to code them. And now we can just write a base agent that has an outer loop and an inner loop, and then you just write things in terms of the loss of the outer loop and the loss of the inner loop. And that's the only thing that you need to do. And it gives you a way, as a group that is working on these things, to scale things up quicker and test more ideas and make more progress. So I think, it's not only about like the type of software that we have, it's also about like getting people excited about an idea and writing new software. The second part, is the bitter lesson. Like we do see that as a community, methods that use more compute get better over time. it doesn't mean that we need to use the compute in a dumb way, right? Like we want to use compute efficiently, and that's exactly like what AlphaGo did to search. Methods that did brute force compute didn't exceed at Go, and we had to get better learning algorithms and write the software to do it. And now we are able to do learning in new domains where it wasn't possible before. I also think that, like the way that the community works, that we focus on specific benchmarks is a way that works as a community. Like even if, specific works at specific times only try to push the SOTA results, as a community, we see progress. So it's not always about like this single paper that gets the state of the art. It's about how we make progress as a community and how we dwell on the ideas that actually stick at the end.
In speaking of the community and so on, do you see any concerning trends right now? Anything where you say, probably too many people are going into this direction, and it's probably not such a good thing. Maybe the rewards, the rewards in the real world aren't really aligned with progress. Do you see anything that worries you at the moment about the research community in RL?
I think that we are a fantastic community. Like, there are so many people coming from so diverse backgrounds, and, people coming with backgrounds in physics and in mathematics, and people that like theory and people that like to do experiments. When we meet at a double-blind review system, sometimes it takes the bad part of us. Like, I like to do experiments, and I will criticize someone that is doing theory, or, we tend to think on things from our own eyes and not as a community. But at the end, I think that we are making great progress, and that, ideas that are developed by different groups eventually end up at the same conferences, and people over time do learn from each other. There are days where I criticize and where, I had a conference where none of my papers was accepted, so I was very anxious, or I don't know. But at the end, I think that we are a great community.
But on the other hand, do you think there are directions where not enough people are going into? Maybe of course, your directions, but do you see other opportunities that you not necessarily want to pursue yourself, but where you think, wow, that's really underexplored?
So, deep learning is a perfect example, because there were times where people were encouraged not to work on that, and today everyone is encouraged to work on that and is not encouraged to work on other things. It's a question of risks. Like if you want to work on something that is not popular, then it's a high risk, high gain, and everyone needs to decide for himself if he wants to do it. Like I engaged in projects that I thought that they are high risk, high gain. At the bottom line, it wasn't that hard risk, and the gain wasn't that big neither. It's something that you need to think about. As a community, we do tend to prefer, incremental works or works that build on previous research. And then again, I think that the important thing is the progress that the community makes, and not the progress that each paper makes. Like you can see many papers that, only changed 10 lines of code, or only wrote a new analysis for an existing algorithm. But then if you look at how things were 5 years ago, then as a community, we made tremendous progress. So, it's not saying that everything's perfect, but I do think that, a lot of things are going.
As a PhD student in reinforcement learning myself, I wonder if it's feasible to go into metagradient work, right?
It's a very good question, because I was in your situation, like, 2 years ago. I also did like a PhD in deep reinforcement learning, and I had to, think about these questions with myself. Specifically for the metagradient work, one aspect of it is that we only use online agents. So, Impala or A3C, it's basically, the less compute-heavy agents that we have. If you compare it to a DQN, then we run 8 times less computations, per data point, because we are not using experience replay at all. So I would say that it is a reasonable agent to work on from a PhD. The second part is that, as a PhD student, it will be harder to get results on all 57 Atari games, and that's perfectly reasonable. And because of that, I think I would recommend to focus on the qualitative properties, like to start with domains that we can carefully think about and gain intuition about what's going on in there, try to, study the very specific aspects. And then, if you can't do the entire 57, then do a subset and it will be perfectly fine. I think it's a bigger question, because if we take the bitter lesson and we want to work on, methods that use a lot of compute, because that's the methods that exceed the most, do we need to use all of the compute that we have at any single experiments that we do? Or can we gain intuition from doing smaller scale experiments and also progress the community from doing so? And I think that there is room for both. If you have access to compute, then you are allowed to do, to study this regime and focus on that, if that's what you're excited about. Because I think that, at the end, that's what will drive us to AGI. But I also think that, we are building on ideas that were developed in more carefully test cases or in the develop intuition, and there's a lot to learn from reading papers like that, and as a community, we can gain a lot from it.
So there was a wonderful article called Deep Reinforcement Doesn't Work Yet by Alex Erpan in 2018, and he was saying basically that he was working at Google Brain for about 6 weeks, and it took him all of that amount of time just to get a basic pendulum policy working, and it still didn't work very well. It's non-stable training, and even if it does work, it probably won't work 70% of the time, and it's not reproducible, and it's sensitive to the random seed and the sample inefficiency and the reward hacking. And the TLDR is that what might not be clear to our audience is that you three are in the top 1%, right? There are kind of power laws in talent, and just to work with reinforcement learning, you have to be incredibly smart. And people like DeepMind and OpenAI, they hoover up all of the talent, and it's one thing for you folks to be working on deep reinforcement learning. But from my position, I'm in industry, and people are excited about reinforcement learning, and they're saying we should be doing reinforcement learning projects. And my advice is, no, don't do it. And people like Microsoft have cottoned onto this, and they've created a reinforcement learning platform called Bonsai, which explicitly abstracts away the complexity of deep RL and uses this concept called machine teaching to kind of create building blocks of how to build DRL agents and so on. In my opinion, it's completely inaccessible to the average person or data scientist in industry. Would you agree with that?
Again, I was in both sides. So I did, a 5-year PhD in a small lab. I had, let's say, 4 GPU machines at the beginning, growed to be around 8. But, a single computer that I bought, I installed the GPU on it. I did the CUDA installation, everything, when it wasn't that easy. And I did deep RL research with this budget. And, I got papers accepted. And I think that some of these ideas helped for the community, or I see people building on these papers. So I don't think it's only about who has more compute, but I think that, if you don't have enough compute, you should be honest about it and constrain yourself to the type of questions that you ask and that you work on. In my case, it was about, trying new domains, trying new ideas, doing some combination of theory and practice, because you can't just, run on the all of the 57 Atari games, as you said. The second thing that happened to me was when I joined DeepMind, and I was able to do all of that. So if I take the StackX paper, for example, I didn't use too much resources for tuning. Actually, the thing that I used the most resources for was to gain better understanding on what's going on. And this was kind of understanding that now when I have the compute resources, I want to communicate the conclusions that I can back to the community. So for example, the ablative analysis that we did, we got, the SOTA performance, we got into it without doing ablative analysis. But once we got these very high scores in Atari, we went back and we said, okay, we have this compute, let's understand how the method works better, and try to communicate that to the communities, and by doing so, try to make them convinced that it's something that they should try themselves. And more generally, I personally think that reinforcement learning works. like every problem that I try to solve, eventually like I managed to get learning or I managed to do something in it. I do think that as a community, it's not at the point where supervised learning is. Basically because we have more challenges and we are looking for solutions to these challenges. If you think about exploration, so we don't have a good solution for deep exploration or exploration with deep nets yet. And there are other problems that we are currently tackling. So it's not clear if we got the optimal solutions, and I do think that we'll see more progress coming up in these years. So it's not industry ready in the sense that you can take off-the-shelf algorithm and it will just work. But I think that if you are a professional and you worked with the systems, then you are very likely to succeed in solving reinforcement learning problems with the algorithms that we currently have.
Speaking of less resources and so on, I was reading also a bunch of papers from back in the day, let's say the 80s and the 90s and so on, and it was incredible to me that sometimes these people, they had an idea of what should be done on a high level. They had a little bit of math, maybe not, and then they had like a little bit of a pseudo algorithm. And if sometimes synthetic, really synthetic data to work this stuff out. And do you think it would be a good thing if we sort of revived a bit more of these sort of concept papers, idea papers, and so on? Or do you think there is something to actually getting down and doing, either real theory or real experiments with limited compute, but still, actually proving something?
We should be honest with ourselves if the way we write papers is actually making us to make progress as a community. I personally very like innovation. So like if a paper had a very good idea back in the 90s, then I think that these ideas will stay and will live with us even when we have more compute. And we mentioned that when I started to do DeepRL, there wasn't DeepRL yet, and I organized a reading group, and we had to read papers from the 90s because there were no papers in the 20s. And we gained a lot of intuition from reading these papers and a lot of inspiration. But when it comes to what should we do today, again, it's what you are excited about. I really like to build systems and to see by my eyes like what they are doing and to debate with myself about it. So that's the kind of work that I'm excited about, that I will read, that I will build on. If you are only excited about getting new ideas, that's also fine. The hardest thing is, like how to evaluate an idea, like if you are only putting it on paper. And that's for the community to decide, right? Like experiments is one thing, math is another way to validate that an idea is interesting. I think it goes back to a discussion we had before about non-stationarity. So I think that many production systems have a non-stationarity aspect in them. So for example, I did an internship at Walmart.com, and we had a catalog with offers. And the catalog was being updated, regularly based on the season, based on the holidays. So what people do is basically they retrain the model, when the data distribution changes. So I think that, there's a big gain to gain from doing a meta-learning approach in these non-stationary systems. Google Maps was another example where there were other non-stationarities in the problem, and metagradients helped. It can also be like the boundness principle that we talked about before. Some resources are shared, and the agent is creating some non-stationarity to the learning dynamics because it's smaller, because it can't perfectly fit the world. So I do see gains from metagradients in other systems that are not completely reinforcement learning systems. But I do see them being used more and more in environments that are more and more non-stationary. And do I trust the code base? I trust it very much. So I basically, most of the new papers that I write, even if they are not with metagradients, I use my own code base because we do have this bias to prefer our own agents because we know like every bit in it. But I found it to be very reliable and very robust.
I was really intrigued by your paper. I think it was in 2011, the one where you wanted to discover structure in the DQN agent, which was trained on breakout. And you did a tSNE projection, and you actually realized that there is a hierarchical state space, right? I mean, how did you even start to go about doing that? That must have been fascinating.
Yeah. So the background is that, we saw the DQN Nature paper, and there was this, fascinating tSNE images in it. And they, when you look at something like that, you basically think that there is some structure in it, like to uncover. And the question was, what kind of structure do we have in it? And my supervisor, I remember, Shai Manor, he sent me an email and he said, like, we should look more and more at structure, at what structure these systems learn. And I had a bias towards, structures that was being explored in the reinforcement learning community. So specifically aggregated states and options. And we just, asked the research question, like, can we find this type of structure in these tSNE images? Or can we do it? So we started with testing type of approach. Like, we just took the system, we built a lot of human knowledge around it. Like, we hand-coded features and we created clusters in the feature space. And we wanted to see if we can, uncover some of the structure. And we succeeded. And we were quite surprised by that. Like, we found one cluster that corresponds to carving the tunnel. Like if you play breakout, then you can carve a tunnel and let the ball go above the bricks. So we were able to uncover a cluster that focused on this. And there were 3 clusters for options that tried to cover the tunnel. And then, we moved to another domain like Sequest, and we found clusters for filling air and for killing monsters and for collecting divers. So like very specific, or hierarchical behaviors. Like a way a human would approach it. So it was all post-analysis, and it was all only handcrafted in that sense. But then we had another follow-up, which was not published in ICML or anything. It was just on archive. And there we wanted to kind of derive an algorithm that will find all of these clusters and all of the options that go between the clusters. And we called it an abstract MDP because it has this, abstract states and abstract options as actions. And we basically wrote an algorithm that fits an abstract MDP to the tSNE image. And we were able to recover exactly the same clusters that we handcrafted with this type of approach. So it was quite nice. I think that on the other hand, it was also disappointing because once we uncovered the structure, we weren't able to do a lot with it. So we tried different things like trying to, control the structure in a way or find some hierarchical policies on this structure. And we didn't succeed too much with this line of work. I worked on it for about a year after we published the first paper. But it was very exciting for me, like the revelations that, the structures that DQNs learn has some temporal aspects in it, and you can see it.
So as I understand that there was, let's say, an embedding or a representation which you've learned, and you did a tSNE projection and you saw all of this kind of aggregations of various different state spaces in that game of breakout. But in a way, that's different to the structure in the neural network. So the neural network also learns this entangled hierarchical structure. And is that completely different to the tSNE projection, or is there a relationship between?
So the tSNE projection was just a way, to project the last layer of the DQN into a 2D representation. So we can look at it as humans because, we are limited to look at things at higher dimensions and see if we can find the further structure in it. So, this, because it's the last layer, it includes in itself like higher level features of behavior because they are very close to the Q prediction. And another work that we did was to try to do better control on top of this representation. So we had a follow-up paper at NeurIPS where we, applied a linear function approximation algorithm that is called least squares policy iteration on top of this representation, and we did got slightly better results from doing it. So I guess that my main takeaway from this type of works was that there is interesting structure that is being encoded, but it's still not clear how to use it or what to do with it. Which, like if you take a fast forward to what we do with metagradients, we encode the knowledge in a way that we can use it or we know how to use it. So the architecture changed, the algorithm changed to a way that allows us to, leverage all the structures that we discover.
Fascinating. Well, Dr. Tom Zahavy, it's an absolute pleasure and an honor. Thank you so much for joining us today.
Thank you very much.
Thank you.
I really hope you've enjoyed the show today. We've had so much fun making it. Remember to like, comment, and subscribe. We love reading your comments, and we'll see you back next week.